Hello. Our lecturer today is Irena Penev. She is an assistant professor in the Computer Science Institute of Charles University from Czech Republic. And her main research interest is structural graph theory and algorithmic graph theory. Today, she will talk about coloring certain even hole free graphs. So, Irena,
Thank you.
go ahead.
Thank you. Okay, so thank you for inviting me. The first thing I'd like to do is just to define certain very basic notions. I think probably most of you are familiar with this, but just in case. So first of all, we're going to need the concept of an induced subgraph. So what's that? Well, you start with some sort of graph, and then you take some of its vertices, perhaps all of them, perhaps not. And then you take all the edges that you had in the original graph between the vertices that you selected. So here's an example of an induced subgraph. This red graph is an induced subgraph of this big graph. But for example, this red graph over here is not an induced subgraph of this graph. Why? Well, because you selected this vertex and this vertex, but you have this edge that is not red. Okay, so it was in the big graph, but not in the small graph. So this is not an induced subgraph. It's a subgraph, but not induced. Okay, and then we have this concept of H-free graphs. We have graphs G and H, and then G is H-free if G does not contain any isomorphic copy of H as an induced subgraph. And you can generalize that for families of graphs. If you have a graph G and a family of graphs F, then G is F-free if G is H-free for every graph H in F. Further, we have this concept of a hereditary class. So what's that? Well, that's a class that's closed under isomorphism and induced subgraphs. That is to say, it's a class such that whenever it contains a graph G, it also contains all isomorphic copies of induced subgraphs of that graph. To state the obvious, if you have some family F, the class of F-free graphs is hereditary. How so? Well, because if you have a graph that's F-free, then obviously all its induced subgraphs are also going to be F-free. Okay, so the next thing I'll be mentioning repeatedly is this notion of a hole. So what's a hole? Well, that's simply an induced cycle of length at least 4. And then you have odd holes and even holes. That's just according to the parity of their length. So even hole, odd hole, odd hole. Okay. Now, as you probably, most of you anyway, know, graphs that contain no holes are called chordal. And again, when I say it doesn't contain a hole, it's as an induced subgraph. So graphs that do not contain any induced cycles of length at least 4, they're called chordal. So that's a famous class. But also we have these odd hole-free graphs. So that's graphs that do not contain any odd holes. And similarly, even hole-free graphs. So graphs that do not contain any even holes. And then I'll also be talking about coloring. So what's a coloring? Well, what you do is you take a graph and then you color its vertices. And what you want is that whenever you have two adjacent vertices, they get different colors. So this is an example of a coloring using 3 colors, this 1, 2, and 3, or red, blue, and green if you prefer. And then, of course, we have this notion of a chromatic number, right? The chromatic number, that's just the smallest number of colors that you need to color your graph. And it's pretty easy to see that this graph over here actually has chromatic number 3. I just presented a coloring with 3 colors, and you can check that you can't do any better than that. Okay, so those were some very basic notions. And now let me give you just quickly a talk outline. So there will be 3 parts. The first part is going to be about a paper that appeared last year over in the Journal of Graph Theory. It's a joint work with Valerio, Boncompagni, and Kristina Vušković, and it's called Click-Cut Sets Beyond Chordal Graphs. And that's something on what we call Truemper configurations, and you'll see what that is in just a second. The second part is essentially a continuation of the first, and it's about coloring rings. What are rings? Again, I'll tell you what rings are, but it's something that comes up in this first part of the talk, and again, you will see that. And then the last part, the third part of the talk, will be on coloring even hole-free graphs of stability number at most 3. What's stability number? So a stable set is just a set of pairwise non-adjacent vertices. So the stability number is just the largest size of a stable set. So stability number at most 3, it means that, well, you can't get 4 pairwise non-adjacent vertices. That's what stability number at most 3 means. Okay, so let me start with this first part. Clique cut sets beyond chordal graphs. So what we did was we studied several classes of graphs that are defined by forbidding as induced subgraphs certain Truemper configurations. And Truemper configurations, those are thetas, pyramids, and prisms, and wheels. And these first 3 are called 3-path configurations, or for short 3PC. Now, if you don't happen to know what these graphs are, don't worry, I'll tell you in just a little bit. But before I do that, I just wanted to mention that Truemper configurations, they have played an important role in the study of a variety of complex hereditary graph classes. So for example, perfect graphs, even whole free graphs, and others. And sometimes they appear as forbidden substructures, so you can't have them as induced subgraphs. But other times they can appear as induced substructures, and then you can use them in order to decompose your graphs, in order to prove decomposition theorems. And what are decomposition theorems? That's just some sort of theorem that tells you how you can break up a graph in your class into smaller pieces in some sort of convenient way. And you'll see examples of this in just a second. Okay, now, if you'll allow me to jump ahead, this is precisely what's going to happen in part 3 of the talk. Part 3 of the talk that's actually coloring those even whole free graphs of stability number at most 3. Let's just jumping ahead. Okay, now let me actually tell you what Truemper configurations are. Now, I already said that we have 2 types. We have these 3-path configurations, or 3PCs for short, and then we have wheels. So let's first look at the 3-path configurations. So those are thetas, pyramids, and prisms. So here, this kind of full line that represents just an edge, and this dotted line that represents a path that has at least one edge. And that happens in all 3 of these graphs. Why are they called 3-path configurations? Well, because you have either a vertex and a vertex, or a vertex plus a triangle, or a triangle plus a triangle, and then you have 3 paths between those. So that's what happens in each of these 3 cases. So those are our 3-path configurations. Now, here's an observation. Every 3-path configuration contains a hole. Remember, a hole is an induced cycle of length at least 4. And as a matter of fact, it contains exactly 3 holes. And how so? Well, let's look at this data. You have these 3 colored paths. Just take any 2 of them, let's say red and blue. Well, they together will induce a hole. Okay, so you have 3 ways of choosing 2 paths, so you get exactly 3 holes. And it's going to be similar over here. You could again choose one path here, another path here, and then together with this edge, you get a hole. Okay, and you can do that for all 3 combinations of these paths, and similar thing over here. Notice that even whole free graphs are theta prism free. Why? Well, because if you have a theta or a prism, then you're going to have an even hole in it. Why? Well, again, let's look at the theta. You have these 3 paths. 2 of them are of the same parity. So let's say red and blue. And so put them together, you're going to get an even hole. And similar over here. On the other hand, odd hole free graphs are pyramid free. Why? Well, because in a pyramid, again, 2 of these colored paths are of the same parity. So let's say this red and blue. And so same parity plus same parity that's even, this one edge, odd. Okay, so every pyramid has an odd hole, and consequently, odd hole free graphs are pyramid free. And if you happen to know what Beer graphs are, if you don't, it doesn't matter. But in particular, Beer graphs are pyramid free. Okay, so just a little bit of algorithmic background. You can detect a theta in polynomial time. You can also detect a pyramid in polynomial time. And actually, this detection of pyramids, so it played an important role in the recognition of Beer graphs, and more generally in the recognition of odd hole free graphs. Now, Beer graphs, well, Beer graphs are actually the same as perfect graphs via the strong perfect graph theorem. Okay, so maybe you know what those are. If you do, well, okay, if you want to recognize these perfect graphs, these pyramids are actually quite important. So this recognition algorithm is it's pretty important. On the other hand, if you want to detect prisms, that's actually NP complete. So that's what we know about the detection of these 3 PCs. And now let me move on to wheels. So that's another type of Truemper configuration. So what's a wheel? So what you do is you take a hole, right? So it's an induced cycle of length is 4, and then you take one other vertex, and you make sure that that new vertex has at least 3 neighbors in the hole. So here are some small wheels. Okay, so those are wheels. Now detecting a wheel is NP complete. And I just wanted again to mention that these wheels, they played an important role in the proof of the decomposition theorem for Beer's graphs. And that decomposition theorem for Beer's graphs is the most important ingredient in the proof of the strong perfect graph theorem. So these are structures that actually appear quite a lot in structural graph theory. Okay, now Truemper configurations, what are those? I already said it, but let me say it again. So those are 3 PCs. 3 PCs are thetas, pyramids, and prisms, and also wheels. Now, a remark, every Truemper configuration contains a hole. For 3 PCs, I explained that. Right? For 3 path configurations, I explained that. For wheels, that's just part of the definition. Consequently, no chordal graph contains a Truemper configuration. Now remember what chordal graphs were. Chordal graphs were graphs that contained no holes. Okay, so if you contain no holes, then you do not contain a Truemper configuration. So here's an example of a graph that is not chordal. Why is it not chordal? Well, because of this hole over here. This, on the other hand, is chordal. Notice that it still has that same cycle, but it's not induced. Okay, so this is something that's chordal. This is not chordal. All chordal graphs, again, well, if you're a chordal graph, then you do not contain any Truemper configuration. Now, for chordal graphs, this is one of the first decomposition theorems in graph theory, not difficult to prove. It says that every chordal graph either is complete or it admits a clique cut set. Complete graph, what's that? Well, that's just a graph in which every 2 vertices are adjacent. And what's a clique cut set? Well, a clique cut set is what I drew over here. So you have a clique. So in my pictures, these kinds of shaded disks, they represent cliques. Cliques, that's just sets of vertices that are pairwise adjacent. So you have this kind of clique. It may possibly be empty. That's okay. And then you can partition the rest of the graph into 2 sets. The other vertices into 2 sets, A and B, non-empty, and you don't want any edges between them. Okay, so if you have something like that, then this C is called a clique cut set. And as I said, this C may possibly be empty. That's okay. So if you have a graph that's disconnected to begin with, then the empty set counts as a clique cut set. And once again, we have this famous decomposition theorem for chordal graphs. It says that every chordal graph either is complete or it admits a clique cut set. Okay, now the next thing that you might ask is, well, can we somehow generalize this? So if you have a graph that, I mean, if you look at the class of graphs that do not contain any Truemper configurations as induced subgraphs, then as a subclass, you get chordal graphs. So what happens if you look at this bigger class? So you do not have any Truemper configurations, again, as induced subgraphs. Well, you actually get a very similar decomposition theorem, except that you have one extra outcome, which is this outcome that G is a hole. So once again, if you have a graph that's 3PC wheel-free, that is to say a graph that does not contain any induced Truemper configurations, then it's either going to be a complete graph, that's exactly what you had over here, or it's going to be a hole. Okay, so that's another outcome. And then, so those would be somehow the basic graphs that you can get. Or it's going to admit this decomposition. So it's going to admit a clique cut set. So that's the same thing that we had for chordal graphs. This is not my theorem. This is a theorem that was proven by these 4 people 20-something years ago. Okay, so what did we do? Well, we actually wanted to generalize that result over here. And how do we generalize it? Well, over here, we forbade, or they forbade, all 3 PCs, so all thetas, pyramids, and prisms, and all wheels. And then we wanted to generalize this by allowing certain kinds of wheels in our class. Okay, so what kinds of wheels? Well, we're going to break wheels up into 3 types. The first type are universal wheels. So what's that? Well, that's what you see in the picture. You take a hole, and then you have this extra vertex, and it's complete to the hole, meaning adjacent to everybody in the hole. So these are some small universal wheels. And then we have twin wheels. And again, that's what you see in the picture. You have a hole, and then you have this extra vertex. And this extra vertex has exactly 3 neighbors in the hole. And those 3 neighbors have to be consecutive. Okay, so these are some small twin wheels. And then finally, we have proper wheels. What are proper wheels? Well, proper wheels are wheels that are not universal and they're not twin. Okay, so what did we study? Well, we studied, again, several classes of graphs that are defined by forbidding certain, not all, Truemper configurations. The first class we studied, this is the biggest class that we studied, is this class GUT. So that is the class of all 3PC proper wheel free graphs. Okay, so what does that mean? Well, that means that the only Truemper configurations that you can have in graphs in this class are the universal wheels and the twin wheels. And that's where this UT comes from. So universal wheels are allowed, twin wheels are allowed, all other Truemper configurations are forbidden. So that's the class GUT. And then we have this class GU. So that's the class of 3PC proper wheel twin wheel free graphs. So over there, you may have universal wheels. So that's this U for universal wheel. You may have universal wheels, but you forbid configurations. And then similarly, we have this class GT. And what's that? Well, that's 3PC proper wheel universal wheel free graphs, meaning you may have twin wheels, but you cannot have any other Truemper configurations. So those were 3 classes that we studied. And now here's just a small observation. Chordal graphs. Chordal graphs are a subclass of each of these classes. Okay, and now these classes, I mean, they're incomparable, right? Neither is a subclass or the other, but obviously these 2 classes are both subclasses of this big class. So what did we do with this? Well, we obtained certain decomposition theorems and also certain algorithms for these classes. Now, how about decomposition theorems? So what did we prove? Well, the decomposition theorems, I'm going to state them, but they're a little bit complicated to state because I have to introduce certain kinds of graphs. So let me explain the shape, if I may put it that way, of our decomposition theorems. So they all say something like this. Every graph in my class, for each of these classes, every graph in my class is either somehow basic, some sort of well-understood kind of graph, or it admits a decomposition where the decomposition is the clique cut set. So it's going to look similar to what we had for chordal graphs. So chordal graph said you're either basic, and basic in the case of chordal means complete, or you admit a clique cut set. Well, it's going to be same here, except that basic no longer means complete. It means something more general than that. So here are the theorems, except of course you don't understand them. They're all of the same form. So for example, we have this decomposition theorem for this class GUT. Okay, it says something like every graph in this class either belongs to BUT. What's BUT? I haven't told you yet, but it's some sort of basic class, okay, that I need to define, or it admits a clique cut set. And for the other 2 classes, it's the same, except that their basic classes are different. And I need to tell you what those are. Okay, so again, the shape of these theorems is the same. They all involve clique cut set decompositions, but the basic building blocks are different. And again, I haven't told you yet what those are. Okay, so I need to tell you what the building blocks are. The first thing that I'll need is the concept of an anti-component. And what's an anti-component? Essentially, that's a component in the complement. So what I have is something like this. I have a graph. Okay, now take the complement, find its components. Here are the components. Go back to the graph. Well, those components correspond to the anti-components. Okay, so just as a graph is a disjoint union of its components. So it's going to be the join. It's going to be the join of its anti-components. Okay, so we have these anti-components over here, and what happens with the anti-components? Well, they're all complete to each other, meaning you have all possible edges between any two anti-components. You have trivial and non-trivial anti-components. Trivial ones, that's the ones that have only one vertex. So here's a trivial anti-component, another trivial anti-component, and non-trivial, at least two vertices. So these are the non-trivial ones. And notice that if you take all the trivial anti-components together, well, they're complete to each other. So together they will form a clique, and they're complete to everything else. So what you get is a clique that's complete to everything else. So you take the union of all the trivial anti-components, you get a clique complete to the rest of the graph. Now, what you will hear me say repeatedly in this talk is something like this. Q is the only non-trivial anti-component of G. What does that mean? Well, the first thing that it means is that this Q is, well, first of all, it's some sort of anti-connected graph. What does anti-connected mean? Well, it means if you take the complement, you get the connected graph. And well, non-trivial means it has at least two vertices. Okay, so that's the first thing that it means. And the second thing that it means is that this Q, this graph Q, well, either this graph G, the big graph G, is actually equal to this only anti-component Q, or I can obtain G by taking this Q and then adding a clique and then adding all possible edges between Q and G. So you will hear me say this repeatedly. Q is the only anti-component, non-trivial anti-component of G. Again, that just means we're anti-connected, meaning the component is connected, and either my whole graph is that Q, or I can obtain the whole graph by taking this Q and then taking a complete graph and then adding all the possible edges. Okay. So next, I will need the concept of K hyperholes and K hyper antiholes. So what are those? So that's actually pretty easy. What you do for these K hyperholes is you take a hole. So remember, hole of length K, and that just means an induced cycle of length K. K has to be at least 4. And then you just blow up each vertex to a non-empty clique. And by blow up, I mean replace the vertex by a clique. And then if you had an edge between two vertices in your hole, just add all possible edges between the corresponding cliques. And if you didn't have an edge in the original hole, then don't put any edges. And then how about K hyperantiholes? Well, it's the same thing, except that you start with antiholes. What are antiholes? Antiholes are just complements of holes. So you're taking the complement of a hole, and then you blow up each vertex to a clique. So that's a K hyperantihole. I mean, K being the length, or rather the number of vertices of the antihole. So I'll need those two concepts. And then I'll need something called a K ring. And remember, the second part of my talk is going to be on coloring rings. So this is the concept that we're going to need. So what are K rings? I wrote the definition over here, but don't look at the definition. Don't look at the definition, look at the picture. What you do is you take K is at least 4, K cliques, non-empty, okay? You arrange them in this kind of circular order. And then between any two adjacent cliques, you may have edges, but if they're not adjacent, you don't have any edges between them. And furthermore, whenever I take any one of these cliques and zoom in, so this is, let's say, xi, any one of these, and then I look at the one on the left, the one on the right, what I can do is I can order the vertices in this clique. Now, you don't see any edges inside this clique. It's a clique, and the reason there are no edges in it is because I don't want to clutter the picture. But you can order the vertices inside this clique in such a way that their closed neighborhoods are nested. So the one on the bottom, the vertex on the bottom has the most neighbors, and then the next one up has some sort of maybe fewer neighbors. So it's some sort of subset. Okay, and then you go up, so on. So you get fewer and fewer neighbors. You just get this nested sequence. And furthermore, there's this technical condition that the one on the bottom, so the one with the most neighbors, actually has to be complete both to the left and to the right. So this vertex on the bottom is adjacent to everybody here and also to everybody there. So that's a ring. And notice that rings actually generalize these hyperholes, right? This is a special case of a ring. Right? Nobody says that these are not allowed to be complete to each other. They're allowed to be complete to each other. So this is just a generalization of hyperholes. Okay, so now I can actually tell you what our decomposition theorems said. Now, the first one was for this class GUT. Let me remind you, GUT means you may have universal wheels, you may have twin wheels, but you can't have any other Truemper configurations. And the decomposition theorem said that every graph in this class either belongs to this class BUT or admissively cuts it. What's BUT? So that's some sort of corresponding basic class. Now, this basic class consists of the following kinds of graphs. So the first is the following. The first type of graph is the following. So graphs that have exactly one non-trivial anti-component, and this anti-component is a ring of length at least 5. And remember what that meant. It meant that either G is a ring of length at least 5, or it can be obtained from such a ring by adding a clique and then making that clique complete to your ring. The second possibility is that G is a long hole K23 C6 complement free. Long hole is a hole of length at least 5. So that's the second type of basic graph. And the third one are graphs whose stability number is 2. And then you want every anti-component to be either a 5 hyperhole or a C5 C6 complement free graph. So that's the basic class that we got. And now what you're going to tell me is that this is not a very nice decomposition theorem. And I'm going to tell you you're right. It's kind of an ugly decomposition theorem. But even though it's kind of ugly, it's actually very useful. And the reason that it's very useful is that you can use it as a starting point for proving much nicer decomposition theorems, such as the two that come next. Okay, so now here's a decomposition theorem for the class GU. GU, that is the class of graphs that may have universal wheels, but they may not have any other Truemper configurations. Again, this decomposition theorem says that every graph in this class either belongs to this basic class BU or admissively cuts it. What's BU? Okay, so that's graphs that satisfy one of these two things. The first is that G has exactly one non-trivial anti-component, and this anti-component is a long hole. In other words, you take a long hole, which is a hole of length at least 5, and then possibly you add a clique and make it complete to the hole. Okay, so that's the first possibility. And then the second possibility is that all non-trivial anti-components of G are isomorphic to K2 complement. K2 complement, that's just the edgeless graph on 2 vertices. So this 2 means that you take a bunch of these K2 complements and then a bunch of these just single vertices, and then you make them pairwise complete to each other. So that's the second possibility. So that's the decomposition theorem for the class BU. And finally, the decomposition theorem for the class GT. GT, that's graphs that may have twin wheels, but they can't have any other Truemper configurations. Okay. So graphs in GT either belong to BT or admittedly cuts it. What's BT? Well, BT is the class of all complete graphs, rings, and 7 hyper antiholes. Okay, so that's what we had. So those are my decomposition theorems. And what did we do with them? Well, we got these algorithmic results using these decomposition theorems. So we looked at the recognition, and then the maximum weight stable set problem, the maximum weight clique problem, and then the optimal coloring problem. And this is the table that we got. One of these was already known just from these 4 people, but all the other results are new. So we can recognize them all in polynomial time. And then we can, for these 2, we can do the maximum weight stable set. For the maximum weight clique, well, one is NP hard. That's the one where we had a ugly decomposition theorem. And then for the nicer ones, we can get polynomial time. And then for coloring, well, it's known for these universal wheels, right? The one that contains where you can have universal wheels, but no other Truemper configurations. And what we had was, well, we had question marks for the other 2 classes. And how did we do this? Well, obviously, we use our decomposition theorems. Now, remember our decomposition theorems, the decomposition in our decomposition theorems is that clique cut set. And for those clique cut sets, we use algorithms for clique cut sets that have been known since the 1980s. And then we also use a coloring algorithm for hyperholes, just produced about 20 years ago, and also a variety of algorithms for handling chordal graphs. So those are very well known. And now I would actually like to draw your attention to one of these question marks, namely this. And so the question is, why is it that we didn't know how to color this class? Well, here's my decomposition theorem once again. So this is my class GT, so the class of graphs that may contain twin wheels, but no other Truemper configurations. We had a decomposition theorem for it. So we were either basic or admitted a clique cut set. Basic meant either complete or a ring or a 7 hyper antihole. So why couldn't we color it? Okay, so what was the problem? Now, clique cut sets were not a problem because, as I said, for clique cut sets, yeah, we can handle them using these tools developed by Tarjan quite some time ago. Complete graphs are obviously not a problem. Okay, we can easily color them. 7 hyper antiholes and more generally hyper antiholes of whatever length you like, they're also not a problem. Why are they not a problem? Well, because if you look at the stability number, what is it? It's at most 2. Okay, so if the stability number is at most 2, well, you want to color. All the color classes are going to have size either 1 or 2, and you want as many of size 2 as you can. So what does that reduce to? We'll take the complement. Okay, you want to find the maximum number of, you want to find the maximum matching, basically, in the complement of the graph. And that just translates to an optimal coloring of your original graph. So those the edges of the maximum matching will be those classes, color classes of size 2, and then those 1 vertex classes will be just all the vertices that were not endpoints of any edge of the matching. So can we find the maximum matching in a graph? Yes. So that's also been known for quite some time. Okay, so clique cuts, it's not a problem. Complete graphs, not a problem. 7 hyper antiholes, not a problem. Rings, a problem. And that's actually what we wrote a whole new paper about. Okay, so with rings, that's going to be part 2 of the talk. But let me just remind you once again very quickly of what rings were. So we had a bunch of, okay, at least 4, arranged in this circular order. Whenever you zoom in on any one of them, so this is a clique, I know no edge is drawn, that's because I don't want to clutter the picture, but it's a clique. You can order the vertices in such a way that the closed neighborhoods are nested. Plus, the one with the most neighbors, the one on the bottom, is complete to the left and complete to the right. So that was a ring. And we had problems coloring rings. That's why that class GT, we didn't know how to color it. And then there was a second paper. Okay, there was this second paper that we had, and I'm just going to talk about it in just a minute, that actually shows you how to color these rings. Okay, now, the first thing I should say, just very briefly, recognizing rings is not a problem. So that can be done in quadratic time. So that we knew in this first paper, just inherited from the first paper. The problem was coloring. Okay, so we want to color rings. Okay, we want to color rings. So how do we color rings? Well, you have 2 types of rings. You have even rings and odd rings. Even rings, what does that mean? Well, it means that the number of these cliques is even, and odd is when it's odd. Okay, so coloring even rings, that's actually is just an exercise. Why? Well, okay, let's say this is one of these. Call it this is some xi, and then this is the next one, xi plus 1, and let's say I is odd. Okay, so how do I color? Well, here I just start from the bottom and I assign colors 1, 2, and so on. And here I start the other way around. I start with omega, so it's the clique number, and then omega minus 1, and so on. And that actually works. That's an optimal coloring. And the only thing that you might ask is, well, wait a minute, how do you find omega? That's actually easy, because take any vertex in the ring, let's say somebody here, and then you look at its closed neighborhood. Well, it doesn't have any holes. If it doesn't have any holes, what does that mean? It's chordal. Well, if you're chordal, can you find a clique, the maximum clique in it? Yes, of course. Okay, so that's been known for quite some time. So you can find the maximum clique in every closed neighborhood. Okay, so do that for every closed neighborhood, and there's your maximum clique. Okay, so you can find omega without any problems. And once you've done that, you just color your even ring in this way, and you can quite easily check that this actually works. Just a little bit of an exercise. But this fails completely. Okay, it's just totally fails if this happens to be an odd ring, meaning if we have an odd number of these cliques. So the question is, what do we do then? Okay, so that's basically the subject of this second paper and of this part 2 of the talk. So again, reminder about K hyperholes. So that's when you take a hole and then blow everybody up to a clique. Also a remark, if you have a ring, okay, then every hole of that ring is of the same length as that ring, meaning all the holes that you can possibly get look like this red thing, meaning you take one vertex from each clique and then you have the edges as represented. So notice in particular these odd rings. Well, odd rings will have only odd holes being of the same length as the ring. In particular, they're even hole free. So these odd rings, which are of interest to me, they're a particular kind of even hole free graphs. Okay. So now this is the main result on which our coloring algorithm depends. It turns out that for every ring, the chromatic number of the ring is equal to the maximum chromatic number of a hyperhole in that ring. Now, why is this nice? Well, the reason this is nice is because there's a nice formula for the chromatic number of a hyperhole. Okay, that's not due to us. That's due to these two people, and it is this. So for a hyperhole, its chromatic number is the maximum of its clique number and of the number of vertices divided by the stability number. And notice that both this and that, I mean, if you forget that this is a hyperhole, both this and that are actually trivial lower bounds on the chromatic number. And what this theorem from 20 years ago says is that actually this trivial lower bound, if you take the maximum, right, then that's actually equal to the chromatic number of the hyperhole. Okay, so you put this main theorem together with this theorem, and you get this nice formula for the chromatic number of a ring. The chromatic number of the ring is the maximum of its clique number, and then this. So you look at all the possible hyperholes in the ring, okay, and then the number of vertices divided by this number, and that's just the formula. That's just the formula for the chromatic number of a ring, and we use this to color rings. I'm not going to tell you anything about the proof of this. It's too complicated. I do want to talk about some consequences of it, and this one I'm just going to skip. I want to talk about coloring. Now, we got a coloring algorithm, an optimal coloring algorithm for rings, and it takes n to the 6th time. I'm also not going to tell you anything about this coloring algorithm. What I am going to tell you is something that's a bit easier. And what is that? Well, that is an algorithm that's faster, it's cubic, that actually computes the chromatic number of a ring. These two are independent. This is significantly easier. And this is very nice. The second one is very, very nice. And let's see how we do that just very, very quickly. So here's our corollary. This gave us the chromatic number of a ring, a formula for the chromatic number of a ring. So what do we need to do? Well, we need to find the clique number. I remember I explained how to find the clique number, just a business with closed neighborhoods being chordal, and then you can find omega in each of them. So that's easy. Okay. And then what you need to do is you need to find this number. And what does this reduce to? Well, you just need to find the hyperhole of maximum size. Okay. So you need to find a maximum hyperhole in your ring. Once you have this number and once you have the size of the maximum hyperhole, you just plug in this formula and you obtain the chromatic number of a ring. So how do we find the maximum hyperhole? Well, we reduced this problem to ON, shortest path problems, and each of them can be done in n squared time, and then together you get n cubed. So how do we do this? So computing maximum hyperhole in a ring. Well, the first thing we want to do is we want to notice that we don't need to actually consider all possible hyperholes. We only need to consider those that we call normal. What is normal? So what you're going to get is something like this. Now we have this ring, and now I'm imagining, remember that we had that sort of ordering of the vertices, nested close neighborhoods, and I'm imagining that the one on the bottom has the most neighbors and so on upward, and the same thing in all of these. So my normal hyperholes are hyperholes that look like this. I have some sort of hole, and then I take all the vertices below it in my ordering. So those are the normal ones. And it's pretty easy to see that every maximum hyperhole, in fact, every inclusion-wise maximal hyperhole is going to be normal. So I just need to find the maximum normal hyperhole. So how do we do that? Well, okay, what I do is I unwrap my ring as follows. So I had remembered these x's. So here they are again, okay, except that I added one more, and this one is a copy of the first one. Now, inside the x's, I delete all the edges. Now there's table sets. And then the next thing that I do is the edges that I had between the x's, they now turn into arcs. So I direct them from x1 to x2 and so on. Okay, and then I add weights to these edges. So how do I do that? Well, let's say here I have this one. So again, this is a nested sequence that we had. And let's say this is the pth one in my nested sequence and the qth one over here. So what's the weight of this? Well, I take xi, size of xi minus p. So what is that? The number of vertices that are strictly above this guy, plus the number of vertices that are strictly above this guy. So that's the weight of this edge. So number of stuff strictly above these two. Okay, so that's the weight. And then if you look at any path, any directed path between the jth vertex here and its copy over there, right? So it has to be the vertex plus its copy, not just any vertex here and any vertex here, but this guy plus its copy. And you take any path, it's going to correspond to a normal hyperhole. How so? We'll take this guy plus everybody below it, this guy plus everybody below it, and so on. And then that's it. And this is just the copy. So you get a normal hyperhole. Now, what's the size of that hyperhole? Well, if you just think about it for just a minute, what you see pretty easily is because of the way that we defined our weights, the size of this hyperhole is precisely the number of vertices in the ring minus 1/2 of the weight of this path. Okay, so what do we need to do? Well, we just need to find the weight of the minimum weight path in order to find the maximum hyperhole. And how do we find the minimum weight path, shortest path? We know how to do that. Dijkstra's algorithm allows us to do that. So that's how you find the chromatic number of a ring. Okay, so you do this for all possible choices of this vertex. You find the maximum hyperhole containing this guy and everybody below it and nobody above it. And then you compare all the results and you get your maximum hyperhole. And as I explained, this will then give you the chromatic number of the ring. Okay, so that's all from the second part. And then I realize I'm almost out of time, so I want to talk very briefly about this third part, coloring even whole free graphs of stability number at most 3. So first of all, for these even whole free graphs, they're well studied. You have decomposition theorems for them, recognition algorithms for them. You can find the maximum clique in them in polynomial time. What is not known is whether you can find the maximum stable set in an even whole free graph. Also not known whether you can color them in polynomial time. Here's another thing that's not known. It's not known whether you can color 4K1 C4 free graphs in polynomial time. That's also not known. 4K1, that's the edgeless graph on 4 vertices. And now what I want to look at is the intersection of these two classes. So these graphs and then even whole free graphs. Okay, so what are those? Those are precisely even whole free graphs of stability number at most 3. Okay, now, actually, those can also be thought of as, well, you can define them, the same class by forbidding finitely many graphs. How so? Well, notice that every hole of length at least 8 contains an induced 4K1. Okay, so if you've forbidden 4K1, then you've automatically forbidden all the holes of length at least 8. So these graphs, even whole free graphs of stability number at most 3, are in fact 4K1, C4, C6 free graphs. And now these 1, 2, 3, 4, 5 people asked whether you can color these in polynomial time. So 4K1, C4, C6 free graphs. And it is part of the job How so? Well, what we want to notice, first of all, is what kinds of holes can you have in graphs in this class? There are only two types of holes, either C5s and C7s. And what they looked at were graphs in my class that contain an induced C7. And they could show that clique width of those graphs is at most 26. What's clique width? It doesn't matter. If you don't know what clique width is, it doesn't matter. It's some sort of a width parameter. The reason that I care about it is because if you have graphs of bounded clique width, in this case bounded by 26, then you can find the chromatic number in such graphs in polynomial time. So put those two things together and you get the chromatic number of these graphs can be found in polynomial time. So that's again, even whole free graphs is the built-in number at most 3 that happen to contain an induced C7. But now the question is, what if they don't contain C7? So what about 4K1, C4, C6, C7 free graphs? So these 5 people asked precisely that question. What happens if can you color this smaller class? Okay. And the answer is yes. That's what I did. So I showed that graphs in this class, well, I'd like to say they have bounded clique width, except that they don't. They either have bounded clique width, meaning at most 5, or they contain a simplicial vertex. And what's a simplicial vertex? It's just a vertex whose neighborhood is a clique, perhaps empty, and non-neighborhood is anything you like. Okay, what does this rely on? It's just on a certain decomposition theorem, which sadly I don't think I'll have the time to really show you, but maybe very, very briefly. And then one remark though, you can't improve this theorem. There's no way you can improve this theorem even if you increase this bound of 5 to any number you like. Why? Well, because if you look at 4K1 free quartal graphs, well, they're all in my class. They're all in my class, but these 4K1 pre-quartal graphs, they have unbounded clique width. Okay, so all such graphs are in my class, unbounded clique width. So no, you can't eliminate the simplicial vertex outcome. Okay, so that's what I just said. But this is my theorem. Again, graphs in this class either have bounded clique width or have a simplicial vertex. Simplicial problem for coloring. I told you that graphs of bounded clique width, you can handle them. So together, together those things imply that you can actually compute the chromatic number of these graphs in polynomial time. And then compared with that theorem of those 5 people that I showed you a little while ago, you get that 4K1, C4, C6 free graphs. Well, you can find their chromatic number in polynomial time. What are these graphs? That's precisely the even whole free graphs, so stability number at most 3. Now, there's this nice decomposition theorem for my graphs, which I don't have the time to show you, but I can show you some pretty pictures. Okay, so here's some pretty pictures. This is one type of graph that you can get. So this is something that I call the 5 crown. It's a very special type of ring of length 5, except that over here, they're complete and they're complete. And then you have another kind of graph that you can get, and it's something that's called a 5 basket. And here's my 5 basket. So you get 8 cliques. They're all non-empty except possibly for this one. Maybe this is empty. Pull edges represent complete, right? So for example, all edges between this and this are present. This means they're edges. And again, as in the case of rings, you get that sort of nested neighborhoods here and here. Okay, so that's what this pickly edges represents. So this is a 5 basket, and I said version 1. There's a version 2. What happens with version 2? Well, version 2 is when this guy moves, this F moves, oops, over here, right? So F is either here or here, right? So 2 types of 5 basket. Okay, so what did I get? Okay, let me see. Right. So the theorem that I got was actually a full structure theorem for these graphs, 4K1, C4, C6, C7 free graphs that do not contain a simplicial vertex. Okay, so I got a full decomposition theorem for them. And that says that, or structure theorem rather, it says that such graphs have exactly one non-trivial anti-component, and it's either a 5 basket or a 5 crown. 5 basket being that 8 clique graph that I showed you in the previous slide, and 5 crown, this special 5 ring. And again, what does this mean? That means that you either take a 5 basket or you take a 5 crown. And then, so having taken that, you're allowed to add a clique and make the clique complete to it. Okay, so that's what this second bullet point says. And what the theorem says is that graphs that you can obtain in this way are precisely graphs in my class that happen not to contain a simplicial vertex. So in other words, if you're in my class, then you either contain a simplicial vertex or you can be obtained in this way. And using that, you get that clique width result. And that's not very hard. Okay. Now, the last few comments. That theorem that I mentioned, right? The coloring algorithm for the class. These are, I mean, both for containing and not containing C7. So from that paper, from those 5 people, and from my paper, okay, they both rely on clique width. Now this is very nice because it gives you polynomial time, but what's much less nice is that you get an enormous exponent. Okay, so this is interesting for theoretical reasons, completely impractical, right? You just get a completely some crazy exponent. So the question is, can you do better? And the answer is yes, you can. And that's actually a paper that's still being written. The one with the clique width has been submitted for publication, and this is one that's being written. Now, the first thing is with containing C7. So that is what those 5 people did. They actually got a very, very nice structure theorem for these. And they showed that graphs in this class are precisely those that can be obtained from certain types of small graphs, small being at most 13 vertices, and not just any graph on 13 vertices, just some very limited number of such graphs. And then you blow up each vertex to a clique. So that's what they proved. And then using that, they very cheaply obtained clique width at most 26. However, if you analyze this, you can get a much faster coloring algorithm. And they got this n to the 9th. And I'm very far from convinced that this is somehow best. I mean, if somebody told me, hey, you know, I just used their structure theorem and they got a cubic time algorithm, that won't surprise me, but this is what I got. Okay. And then how about for when you forbid C7? So that's what I got that nice decomposition theorem for. So there, yeah, I could do better. And again, I can't give you the details, but it uses that coloring algorithm for rings. Okay. And what you get is n to the 6th. And I'm going to tell you that that algorithm actually relies on finding the chromatic number of a ring n squared times. So that's n squared times n cube, because I can find the chromatic number of a ring in cubic time. And then once I found it, I only color a ring one single time, which takes n to the 6th. Okay, so this can actually be done in n to the 6th time using that stuff on rings. Except, I'm going to tell you one more thing. That's if you rely on that paper, the second paper, right, for coloring rings. And you get rings in these graphs, but they're very nice rings. They're not general rings. So you get that n to the 6th coloring algorithm for general rings, but here you don't get general rings. And actually in the end, and this I'm still checking all the details, but it's going to be better than n to the 6th, because for the very special rings that you obtain, you can do some tricks and do a bit better. The exact running time to be determined, but it looks like n to the 4th, maybe n cubed, by, again, doing something smart with very special kinds of rings, rather than just using that sledgehammer with general rings. Okay, so n to the 6th when you don't contain C7, n to the 9th when you do contain C7. Together, you get n to the 9th for even whole free graphs of stability number at most 3. If you want to improve this, look at this. It's probably possible to do significantly better. That wouldn't surprise me. I just got 10 to the 9th, but you have a very, very nice structure theorem. And that's it. That's it. So thank you for listening.
Thank you very much for the nice presentation. Are there any questions?
Wait, so I'm getting very... Okay, so Martin and then Blas. Yes.
I have a question and a remark. Could you please show us the table at the, I think it was at the end of part 1 when you had those classes and algorithmic problems.
Mm-hmm. Yep.
Actually, maybe
except that this is now known using rings.
Okay.
This is now known.
What about the first question mark on that one? Yes.
This one? Or this one?
Yes, I think so for the weighted stable set problem, I think there were some recent results, at least on archive, solving the problem in long haul free graphs. That probably you could apply here using your decomposition theorem.
I see. So for long haul free.
Abrishami, Chudnovsky, Filipchuk, Zhezhevsky, and Seymour, I think, solved it in polynomial time for long haul free graphs. And I think this is the only complicated basic class in your case.
That's
so probably it would imply.
Yeah, okay, so this one, yes, and this one, yes, and rings we know. So yeah, you're right. So yeah.
So probably you can settle that in the polynomial direction. And the question I had, so I was interested, you mentioned at the end you used some click width results, but what about tree width of these graph classes? Do you know anything about the relation with the click number?
I mean, I don't. I just know that definitely it's unbounded. I mean, like in absolute terms, because you can have large cliques.
Yes,
that's obvious. I do not know whether you can get tree width as a function of the click width. Not click width, but
click number. So it seems to me that in the two smaller classes, this is the case, but for the larger one, I don't know. It would be interesting. And the related question is, but maybe it's already solved. K coloring for fixed K.
For which one?
Well, when coloring is polynomial, of course, K coloring is polynomial. So I guess there's only one open case left.
Yes, this one. But wait, so this one, okay, so wait a minute. So you told me that the long haul, that was for the stable set?
Yes.
Yes, okay. Yeah, I mean, again, you would have to, wait a minute. I mean, you'd have to color these, right? So how do you color these? I mean, the thing is, this is not, I mean, this is, I don't know what these things look like, right? I mean, this is the best that we were able to do, but this is not,
yes.
This is not very nice.
Still a complicated class.
Yeah, it's still a complicated class. And I mean, of course, when you have some sort of subclasses, then you can kind of turn this messy class into something much nicer, and then it becomes, helpful. But if you just want to work with this, yeah. And also, this is the reason actually why you got an NP completeness result. So that, yes. I mean, that second one is actually the reason.
Yeah. Okay. Thank you very much.
Okay. Questions? Any other questions? Okay. It seems that there are no more official questions, so let's finish with the official part of the seminar, but you are all invited to hang a little bit more on a Zoom and chat unofficially. So see you next week, and thank you, Irena, once again for your talk.